The planets in our solar system constitute a diverse group of celestial bodies orbiting the Sun, encompassing 8 primary planets categorized into terrestrial planets, gas giants, and ice giants. This classification highlights significant differences in their composition, structure, and formation processes, with terrestrial planets, Mercury, Venus, Earth, and Mars, being rocky and located closer to the Sun, while gas giants, Jupiter and Saturn, are predominantly composed of gaseous materials and situated in the outer regions. Uranus and Neptune, classified as ice giants, are characterized by their unique compositions of water, ammonia, and methane ices, further enriching our understanding of planetary diversity and evolution. The study of these planets is notable not only for its scientific importance, but also for its historical significance in humanity's quest to understand the cosmos. Early astronomical observations, notably by ancient civilizations, laid the groundwork for modern astronomy, while the advent of advanced robotic missions since the mid-20th century has revolutionized our knowledge of these distant worlds. Noteworthy explorations during the golden age of planetary discovery, particularly between 1976 and 1989, have yielded critical insights into planetary atmospheres, geology, and potential for life, ultimately leading to the emergence of comparative planetology, a discipline that seeks to understand planets through interplanetary comparisons. Prominent controversies in planetary science include debates over planetary classification, particularly regarding the status of dwarf planets like Pluto, which has stirred discussions about what constitutes a planet and how these definitions impact our understanding of the solar system. Furthermore, ongoing research into planetary formation theories, such as core accretion and disk instability, continues to challenge existing models and inspire further inquiry into the origins of celestial bodies within our solar neighborhood and beyond. As research advances and exploration efforts continue, the planets of our solar system remain focal points for scientific inquiry and public interest, inviting deeper exploration into their mysteries and complexities while offering potential insight into the broader workings of planetary systems throughout the universe. Imagine standing on a quiet hill thousands of years ago, long before city lights drowned out the night sky. Above you, the heavens stretch endlessly, a velvet canvas dotted with glittering stars. Most of those stars seem fixed and unchanging, but a few bright points of light with a faint reddish or golden glow slowly drift against the backdrop over nights and weeks. To the ancient Babylonians, Greeks, Chinese, and countless other civilizations, these mysterious wanderers weren't just lights. They were omens, deities, or signs from the heavens. Mercury, Venus, Mars, Jupiter, and Saturn, the only planets visible to the naked eye, were humanity's first known planets, but they were understood only as wandering stars. These early sky watchers meticulously tracked the planet's movement. The Babylonians developed tables predicting their paths. Greek philosophers like Pythagoras and Aristotle debated their nature. Chinese astronomers recorded them in detailed star charts. Planets were woven into myths. Mars became the god of war. Venus, the goddess of beauty, Jupiter, the king of the gods, symbols of cosmic order and mystery. Yet, for all their skill, ancient observers had no way to see these worlds as anything more than points of light. The real transformation wouldn't come until millennia later. Fast forward to the early 17th century. In a small workshop in the Netherlands, a curious instrument of glass and wood is crafted to telescope. It magnifies distant objects, and soon news of this device spreads across Europe. An Italian mathematician named Galileo Galilei seizes upon the idea. In 1609, he built his own telescope and pointed it skyward. What he sees shatters centuries of assumptions: mountains and craters on the moon, phases of Venus, and most astonishingly, 4 tiny moons circling Jupiter. This discovery is a revelation. Jupiter is not alone, and the Earth is not the center of all motion. Galileo's drawings of the Medicean stars, what we now call Io, Europa, Ganymede, and Callisto, show the first evidence that other worlds have their own systems. The solar system is far more complex than anyone imagined. This marks the dawn of modern planetary discovery, where careful observation and technology begin to replace myth and speculation. For more than a century after Galileo, Saturn marked the edge of the known solar system. But in 1781, William Herschel, a German-born musician turned astronomer, swept the sky with a powerful telescope of his own design. One night, he notices a faint disk-like object in the constellation Taurus. At first, he thinks it's a comet. Over time, calculations prove it's something much larger and farther away, a new planet. Herschel names it Georgium Sidus. After King George III, the name Uranus comes later. This is the first planet discovered in modern history, and its finding stirs excitement across Europe. Suddenly, the solar system has grown bigger, but the story doesn't end there. Astronomers notice Uranus's orbit isn't behaving exactly as Newton's laws predict. Something unseen seems to tug on it. 2 mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculate where the mystery body should be. On a September night in 1846, Johann Galle at the Berlin Observatory pointed his telescope to the predicted spot and found Neptune within a single degree of Le Verrier's calculations. This is planetary discovery by pure mathematics, a triumph of human reasoning before the object is even seen. Even after mapping the 8 major planets, astronomers knew the solar system's story wasn't complete. Beyond the orbit of Neptune lay a dark, cold frontier, a region filled with icy bodies and mysterious objects waiting to be discovered. It was here, at the edge of the known solar system, that a young astronomer named Clyde Tombaugh would change our cosmic perspective forever. Working at Lowell Observatory in Arizona in the late 1920s, Tombaugh faced the painstaking task of comparing photographic plates of the night sky, taken nights apart, in search of faint points of light that shifted against the background of stars. His patience, determination, and meticulous attention to detail paid off. On February 18, 1930, he discovered a tiny, distant dot moving slowly across the starry backdrop. This small, icy world was named Pluto, honoring the Roman god of the underworld, a fitting name for a planet dwelling in the dark outer reaches. Pluto is a dwarf planet, about 2,377 kilometers in diameter, smaller than Earth's moon. It orbits the Sun every 248 Earth years, following a tilted, elliptical path that sometimes brings it closer to the Sun than Neptune. Its surface is a frozen landscape of nitrogen, methane, and carbon monoxide ices, with mountains of water ice and plains carved by ancient glaciers. Despite its remoteness, Pluto has 5 known moons, the largest being Charon, which is so massive relative to Pluto that the two bodies orbit a shared center of mass in space. The discovery of Pluto was more than just finding another object. It symbolized the limits of human persistence and ingenuity. Tombaugh's work demonstrated that even the faintest, most distant worlds could be found through careful observation, patience, and innovative techniques. Decades later, spacecraft like New Horizons would reveal Pluto in stunning detail, transforming it from a tiny point of light into a vibrant, complex world with mountains, plains, and potentially even signs of geologic activity. Pluto also heralded a new understanding of the solar system's outer frontier. It is part of the Kuiper Belt, a vast population of icy bodies beyond Neptune, many of which share similar compositions and histories. This discovery expanded our conception of the solar system, showing that the planets we know are only the largest members of a far more intricate and dynamic family of worlds. Pluto reminds us that the solar system has edges yet to explore, and that even the tiniest worlds can teach us profound lessons about the universe. Through all these centuries, planets beyond Earth were still little more than colored specks. That changed dramatically in the mid-20th century. As rocketry and space exploration develop, robotic spacecraft become our new telescopes. NASA's Mariner missions in the 1960s and 70s sent back the first close-up images of Mars, Mercury, and Venus. Suddenly, Mars isn't just a red dot, but a place of canyons and volcanoes. Mercury isn't a featureless speck, but a world of craters. Then comes Voyager. In 1977, twin spacecraft launched on a grand tour of the outer planets. Over the next decade, they revealed Jupiter's swirling storms, Saturn's intricate rings, Uranus's tilted axis, and Neptune's dark, mysterious spots. Moons like Europa, Enceladus, and Titan turn out to be worlds in their own right, some with icy oceans, some with atmospheres, some with geysers spraying into space. The solar system transforms from a simple family of planets into a breathtakingly diverse menagerie of worlds. Just when it seems we've mapped our neighborhood, a new chapter begins. In 1995, astronomers announced the first discovery of a planet orbiting a star like our Sun. It's a hot Jupiter, a giant gas planet orbiting scorchingly close to its star. In 2009, NASA's Kepler Space Telescope launched, scanning hundreds of thousands of stars for the tiny dips in brightness caused by transiting planets. The results are staggering. Thousands of confirmed exoplanets, with estimates of billions more in our galaxy alone. We find rocky worlds, super Earths, mini Neptunes, and bizarre systems unlike anything in our solar system. This is more than just data. It's a revolution in perspective. For most of human history, planets were rare jewels in the sky. Now we know planets are everywhere. The story of planetary discovery has expanded beyond our own star, hinting that the drama of worlds may be universal. The history of planetary discovery is far from over. Today, missions like the James Webb Space Telescope, TESS, and upcoming explorers like the European Space Agency's Plato and NASA's LUVOIR promise to study exoplanet atmospheres, search for signs of habitability, and maybe even detect biosignatures, chemical hints of life. Within our own solar system, missions to Europa, Enceladus, and Titan will probe oceans beneath icy crusts. Each new discovery adds another chapter to a story that began with ancient stargazers and their wandering stars. It's a story of curiosity, patience, and imagination, of humans looking up at the night sky and daring to ask, what's out there? From Babylonian records etched on clay tablets to high-resolution images of alien landscapes. The history of planetary discovery is our collective journey from wonder to knowledge, from myth to science, and from our tiny corner of the cosmos to the infinite beyond. Picture a warm evening on the plains of Mesopotamia more than 3,000 years ago. The Tigris and Euphrates rivers glint under a pale moon. Farmers finish their day's work, and as darkness spreads, the heavens blaze above them with an intensity modern city dwellers rarely see. For the people of this fertile land, the Babylonians, the night sky isn't just a backdrop. It's a living calendar, a storybook, and a cosmic stage where gods enact their dramas. Night after night, generation after generation, Babylonian priests and astronomers climb the high terraces of their ziggurat. These stepped temples double as observatories. From these lofty vantage points, they keep silent vigils, scratching marks on clay tablets to record the movements of stars, the waxing and waning of the moon, and the peculiar wanderings of certain bright points of light. Unlike the fixed stars, these wanderers, Mercury, Venus, Mars, Jupiter, and Saturn, drift steadily against the constellations. They are unpredictable at first glance, sometimes moving forward, sometimes backward, sometimes vanishing into the sun's glare. Yet with patience, patterns emerge. The Babylonians' genius lies in noticing and quantifying these patterns. By the 7th century BC, they had developed a systematic form of mathematical astronomy. They know when Venus will reappear as the morning star. They can predict eclipses with remarkable accuracy. They chart the stations of Mars and the retrograde loops of Jupiter. These aren't mere curiosities. In a world where religion, governance, and astronomy are entwined, Such predictions are tools of power. Kings consult the stars before battles or harvests, and the ability to forecast the heavens gives priests enormous influence. One of their most enduring contributions is the division of the sky into a celestial band. The zodiac split into 12 equal sections. This framework organizes the motion of the sun, moon, and planets, and will later be adopted and refined by the Greeks. Even today, when we speak of constellations like Aries, Leo, or Sagittarius, we echo a system first mapped out under Babylonian skies. The Babylonians aren't alone. In ancient China, imperial astronomers record guest stars, novae, and comets for centuries, while in India, scholars compile astronomical treatises blending observation with philosophical speculation. The Mayans in the Americas developed their own intricate calendars and track Venus with astonishing precision. Across cultures, the same impulse drives people to look up, measure, and seek meaning. Yet in Babylon, something new begins, a shift from purely symbolic interpretation to something recognizably scientific. Their star catalogs, clay tablets like the MUL, a pen, list fixed stars, and planetary paths in a structured way. They create arithmetic schemes to predict celestial events. They're not yet doing physics, but they are laying the groundwork for it. When Greek thinkers such as Pythagoras, Plato, and later Ptolemy developed their own models of the cosmos, they will draw heavily on this Babylonian heritage. The Greek zodiac is essentially Babylonian. The very word planet comes from the Greek for wanderer, but the data behind it was recorded long before on Mesopotamian clay. This era of early observations is like the prologue of humanity's planetary story. We haven't yet built telescopes or spacecraft. We don't know what planets really are, but we've learned to see patterns, to predict, and to pass knowledge down across generations. In the flicker of oil lamps atop cigarettes, the first glimmers of astronomy as a science appear. The year is 1976. In a dusty control room at NASA's Jet Propulsion Laboratory, engineers and scientists lean forward in tense anticipation. On a television monitor, grainy black and white images flicker into view, the first clear pictures from the surface of another planet. After centuries of gazing at Mars through telescopes, humanity has finally touched it, albeit with machines. Viking 1 and Viking 2, two robotic spacecraft launched the year before, are now sitting on the red soil of Mars, their cameras panning across barren plains under a pink sky. The dream of seeing other worlds up close has leapt from science fiction to reality. This moment marks the beginning of what would come to be called the Golden Age of planetary exploration. From 1976 to 1989, an unprecedented wave of robotic missions transformed our understanding of the solar system. For generations, planetary astronomy had been a science of dots and smudges, limited to what telescopes could show us from Earth. Now, with the space age in full swing, spacecraft carry our curiosity across millions and even billions of kilometers, turning abstract points of light into tangible worlds. The Viking landers on Mars are just the opening act. They test the soil for signs of life, measure the atmosphere, and photograph the terrain with astonishing clarity. Suddenly, the canals imagined by 19th century observers vanish. In their place are vast deserts, dried river channels, and hints of a wetter past. Mars is no longer an enigmatic red star, but a geologically complex planet with a history waiting to be unraveled. At the same time, other spacecraft are rewriting our picture of the outer planets. In 1977, twin Voyager probes lifted off on a daring mission, riding a rare planetary alignment that happens only once every 176 years. Their trajectory will allow them to visit Jupiter, Saturn, Uranus, and Neptune in one grand tour. Over the next decade, Voyager 1 and Voyager 2 beam back images and data that astonish scientists and captivate the public. We see Jupiter's great red spot up close, Saturn's rings in intricate detail, Uranus's bizarre tilted axis, and Neptune's supersonic winds. Moons once thought inert reveal unexpected activity. Io spews volcanic plumes. Europa hides an ocean beneath ice. Enceladus and Triton show signs of internal heat. Each discovery raises new questions and expands our sense of what a world can be. This golden age doesn't just give us pretty pictures, it creates a revolution in thinking. Before these missions, scientists studied planets in isolation. Afterward, they can compare them systematically, their atmospheres, surfaces, magnetic fields, and internal structures, giving rise to a new discipline, comparative planetology. By examining how planets and moons differ and resemble one another, researchers begin piecing together how they formed, evolved, and perhaps even how life might arise elsewhere. The impact of this era stretches far beyond the data it collected. It shapes our expectations for future exploration. Concepts like astrobiology, the study of life in the universe, gain traction because the Viking missions show us how to search for biological signatures. The Voyagers, now sailing into interstellar space, carry golden records with messages from Earth, a symbolic gesture of reaching out to the cosmos. Every headline, every image feeds a sense of global wonder. For the first time, humanity is truly a solar system species, seeing its neighborhood firsthand. By the end of the 1980s, our mental map of the solar system had been utterly transformed. No longer do we imagine Mars as a planet of canals, or the outer moons as frozen dead rocks. Instead, we see a dynamic, varied system full of surprises, a system whose complexity mirrors and enriches our own planet's story. The golden age of planetary exploration is more than a historical period. It is the moment when our robotic emissaries became our eyes and ears, carrying human curiosity farther than ever before and laying the groundwork for everything that came after. By the early 1990s, the first golden age of planetary exploration had already changed humanity's mental map of the solar system. We had landers on Mars, flybys of every giant planet, and breathtaking images of alien landscapes. But most of these encounters were brief spacecraft streaking past worlds at thousands of kilometers per hour, snapping pictures in a matter of hours before speeding onward. To truly understand another planet, scientists longed for something more, not a passing glimpse, but a long, sustained presence, orbiters that could watch the same world over months and years. This desire coincided with rapid leaps in spacecraft engineering, new generations of propulsion systems, lightweight materials, computer guidance, and miniaturized instruments made it possible to send heavier, more capable probes across interplanetary distances. With them came a second age of robust planetary exploration, a slower, deeper era where our machines would not just visit other worlds, but take up residence around them. Magellan was one of the first of these new explorers, launched in 1989, and arriving at Venus the following year. It carried a powerful radar system that could see through the planet's thick, sulfuric acid clouds. For centuries, Venus had been Earth's sister planet in size, but an enigma in nature. Magellan's radar mapped 98% of its surface in high resolution, revealing a world of vast lava plains, mountain ranges, and strange pancake-shaped domes. These data shattered lingering Earth like illusions. Venus was not a tropical paradise, but a geologic inferno, a place where surface temperatures could melt lead. As Magellan transformed our view of Venus, Galileo was heading for the largest planet of all. Launched in 1989, delayed by a long and complex trajectory, Galileo finally arrived in orbit around Jupiter in December 1995. For nearly 8 years, it became our permanent outpost in the Jovian system. Galileo watched lightning in Jupiter's atmosphere, mapped its turbulent cloud belts, and made close flybys of moons like Io, Europa, Ganymede, and Callisto. It found evidence of subsurface oceans beneath Europa's icy crust, a finding that ignited new hopes of alien habitats in our solar system. Then came Cassini, the flagship of this new era. Launched in 1997, Cassini entered orbit around Saturn in 2004 and stayed for more than 13 years, longer than any previous outer planet mission. With its cameras and instruments, Cassini revealed Saturn's rings as dynamic laboratories of particle physics, discovered geysers of water vapor and ice erupting from Enceladus's south pole, and dropped the European-built Huygens probe through the orange haze of Titan, parachuting it onto the surface of a world with lakes of liquid methane. Each of these discoveries deepened the idea that even far from the sun, icy moons might harbor conditions suitable for life. Closer to home, messenger Mercury's surface, space environment, geochemistry, and ranging made history as the first spacecraft to orbit Mercury. From 2011 to 2015, it mapped the innermost planet's surface in detail, discovered ice deposits in permanently shadowed craters, and revealed a world far more geologically active and chemically diverse than the barren rock many had assumed. Together, these missions illustrate a shift from snapshots to long-term studies. Instead of brief flybys, orbiters like Magellan, Galileo, Cassini, and Messenger allowed scientists to monitor seasonal changes, magnetic fields, atmospheric dynamics, and geological processes over time. They return terabytes of data, far more than all previous missions combined, enabling scientists to build complex models of planetary formation, evolution, and potential habitability. This second wave of planetary exploration also forged new international partnerships, advanced high-gain antenna technology for deep space communications, and refined the art of gravitational slingshots to save fuel on long journeys. It taught engineers how to design instruments that could survive decades of radiation, extreme cold, and remoteness, lessons now feeding directly into upcoming missions to Europa, Enceladus, Titan, and beyond. In essence, the second age of spacecraft technology was like moving from tourist snapshots to living among the locals. Our robotic emissaries became patient residents, peeling back the layers of our solar system one orbit, one season, one discovery at a time. They showed that each planet and moon is a world with its own story, and that our story as explorers is only beginning. At the dawn of the 21st century, a quiet but profound revolution began in astronomy. For centuries, the only planets we knew were those circling our own sun. Philosophers speculated about other worlds, and science fiction writers filled galaxies with alien landscapes, but there was no proof. Then, in 1995, astronomers Michel Mayor and Didier Queloz announced the first confirmed planet orbiting a sun-like star, 51 Pegasi b, a searing, hot Jupiter racing around its parent star in just 4 days. In that moment, the universe changed. Planets beyond our solar system were not just possible, they were real. Over the next 2 decades, the trickle of discoveries became a flood. Using a variety of ingenious methods, astronomers have now cataloged thousands of exoplanets, more than 3,700 confirmed, and thousands more candidates, with new ones announced almost every month. Each technique works like a different sense organ, revealing unseen worlds in indirect ways. The transit method, pioneered by ground-based observatories and perfected by NASA's Kepler Space Telescope, watches a star's light dip ever so slightly when a planet crosses in front of it. These tiny eclipses can reveal a planet's size, orbit, and even hints of its atmosphere. Gravitational microlensing uses a completely different trick of nature. When a massive object like a star or planet passes in front of a more distant star, its gravity acts like a lens, magnifying the background light and betraying the presence of otherwise invisible bodies. Other methods, like radial velocity measurements, directly detect a star's gentle wobble under a planet's gravitational tug. As technology advanced, astronomers moved from simply inferring exoplanets to actually imaging them. Instruments such as the Atacama Large Millimeter or Submillimeter Array in Chile, with its sweeping fields of giant radio dishes, now peer into protoplanetary disks, vast, dusty rings of gas and rock, where planets are being born. In these glowing, swirling cradles, scientists have caught glimpses of gaps and spirals carved by newborn worlds. For the first time in human history, We're not only detecting planets, but also watching planetary systems assemble in real time. These discoveries are more than numbers in a catalog. They're a revolution in perspective. Kepler and its successors have shown that planets are not rare jewels, but the norm. Most stars probably host them. Super Earths, mini Neptunes, tightly packed systems, and rogue planets drifting alone. All these once seemed exotic. Now they're commonplace. The very diversity of exoplanets forces scientists to rethink how planets form and evolve, and it has sharpened the search for life beyond Earth. When astronomers use next-generation telescopes, like the James Webb Space Telescope, to analyze exoplanet atmospheres, they're not just collecting data. They're looking for chemical signatures that might hint at oceans, weather, or even biology. In a way, this exoplanet revolution is the culmination of everything begun by ancient skywatchers, where the Babylonians tracked wandering stars and Galileo spied Jupiter's moons. Today's astronomers use giant observatories and space-based instruments to track worlds across unimaginable distances. We're still gazing at lights in the sky, but now we can tell you their size, their temperature, their orbit, and sometimes even their color. In the quiet hum of a telescope control room or the swirling data streams from ALMA, we're witnessing the universe's most intimate processes: stars forming, planets coalescing, systems evolving. And this is only the beginning. Upcoming missions like NASA's Nancy Grace Roman Space Telescope and the European Space Agency's Plato will push these techniques even further, surveying millions of stars and characterizing thousands of new worlds. Direct imaging with giant ground-based telescopes and star shades may soon let us see Earth like planets as pale blue dots circling distant suns. We're standing at the threshold of a new era where planetary discovery moves from cataloging to characterizing, and perhaps, one day soon, to finding evidence of life. This 21st century phase of planetary exploration is not a separate story, but the latest chapter in a saga that began under ancient skies. It's a story of steadily sharpening tools, expanding horizons, and relentless curiosity. Our species' ongoing quest to know not just where we are in the cosmos, but who else might be out there. Gas giants, represented by Jupiter and Saturn, dominate the outer regions of our solar system. These colossal worlds formed far from the sun, where temperatures were low enough for vast amounts of hydrogen, helium, and other volatile substances to accumulate. At their hearts lie dense cores, estimated to be about 10 times the mass of Earth, encased in immense layers of gas and fluid. Recent research has revolutionized our understanding of how these giants form. Instead of slow, gradual accumulation, scientists now believe they may develop much more rapidly. This accelerated formation could be triggered by ring-shaped perturbations, areas of enhanced density, in the protoplanetary disk of gas and dust. This process separates the formation of gas giants from that of the smaller, rocky terrestrial planets, painting a picture of a solar system built in distinct stages and regions. Ice giants. Further out still lie Uranus and Neptune, known as ice giants. While they also harbor hydrogen and helium, these planets contain significantly higher proportions of water, ammonia, and methane ices locked deep within. This composition gives them strikingly different colors, densities, and internal structures compared to Jupiter and Saturn. Their formation likely mirrored that of gas giants, but took place under colder and more isolated conditions, resulting in worlds rich in heavier volatiles. This distinction makes ice giants a crucial key to understanding not just our solar system's diversity, but also the wide variety of giant exoplanets discovered around distant stars. Individual planets. Mercury. Mercury is the smallest planet in the solar system and the closest to the Sun. It spins almost upright on its axis and does not experience any seasons. Continually blasted by solar emissions, the intensity of the Sun's rays on Mercury is approximately 7 times stronger than on Earth due to its tenuous atmosphere, known as an exosphere. Mercury does not have weather systems. Temperatures on the planet can soar to a scorching 430 degrees Celsius during the day, while at night, they plummet rapidly to extremely cold levels. Venus. Venus, often called Earth's sister planet due to its similar size and composition, possesses a thick atmosphere composed mainly of carbon dioxide with clouds of sulfuric acid. This dense atmosphere creates a strong greenhouse effect, leading to surface temperatures that can reach up to 467 degrees Celsius, making Venus the hottest planet in the solar system. The atmospheric pressure at its surface is about 92 times that of Earth's, which would crush most human-made probes. Earth is the only known planet to support life, featuring a diverse array of ecosystems and a stable climate. Its atmosphere is composed of approximately 78% nitrogen and 21% oxygen, with trace amounts of argon and carbon dioxide. Earth's weather systems are primarily driven by convection processes within the troposphere, where warm air rises and cool air sinks, distributing heat from the sun. The planet's surface is 71% water, which plays a crucial role in regulating its climate and supporting life. Mars. Mars is often referred to as the red planet due to its iron oxide-rich soil, which gives it a reddish appearance. The planet has a thin atmosphere, primarily composed of carbon dioxide, with temperatures that can vary significantly. Evidence suggests that Mars once had liquid water on its surface, leading to speculations about past life. The planet is home to the largest volcano in the solar system, Olympus Mons, and has 2 small moons, Phobos and Deimos. Jupiter. Jupiter is the largest planet in the solar system, classified as a gas giant with a powerful gravitational pull that has captured over 80 moons. It features a prominent equatorial belt of reflective clouds and is known for its intense winds, which can reach speeds of 402 kilometers per hour. Jupiter's Great Red Spot, a massive storm twice the size of Earth, has persisted for over 300 years and remains a defining characteristic of the planet. Its lack of a solid surface allows storms to rage unimpeded. Saturn. Saturn is renowned for its stunning ring system and is the second largest planet in the solar system. It completes a rotation in just 10 hours, generating wind speeds of up to 1,600 kilometers per hour. The planet has numerous moons, the most notable being Titan, which has a dense atmosphere and liquid methane lakes. Saturn's dynamic atmosphere includes features like the Uranus dark spot, a large swirling vortex observed on its surface. Uranus. Uranus is unique for its extreme axial tilt, which causes its rotational axis to be nearly parallel to its orbital plane. This unusual orientation results in extreme seasonal variations. The planet displays a pale blue-green color due to methane in its atmosphere, which absorbs red light. Uranus has a relatively featureless exterior, though cloud bands have been detected beneath its high haze. Winds on Uranus can reach significant speeds, despite the lack of large cyclonic structures. Neptune. Neptune, the outermost planet in the solar system, takes about 165 Earth years to complete an orbit around the Sun. It has a striking blue appearance, driven by methane in its atmosphere, but is known for its wild weather, including winds that can exceed 2,100 kilometers per hour. Neptune's atmosphere features powerful storms, such as the Great Dark Spot, similar to Jupiter's Great Red Spot, showcasing the dynamic nature of its climatic conditions. Asteroids. Asteroids are primarily found in the asteroid belt, located between the orbits of Mars and Jupiter. This region once contained enough material to potentially form 2 to 3 Earth-sized planets. However, the gravitational influence of Jupiter caused many of these planetesimals to collide and fragment, preventing the formation of larger bodies and leading to the current population of smaller asteroids. These rocky bodies are composed mainly of metals and minerals and can vary widely in size and shape. Comets and meteoroids. Comets, often referred to as dirty snowballs, consist of ice, dust, and rocky material. They originate from 2 primary regions, the Kuiper Belt and the Oort cloud. The Kuiper Belt lies beyond the orbit of Neptune and is home to many small icy bodies, while the Oort cloud is a distant spherical shell surrounding the solar system that is thought to contain numerous cometary nuclei. Meteoroids, on the other hand, are smaller particles that travel through space. When they enter Earth's atmosphere and burn up, they are referred to as meteors, and if they survive the journey to the surface, they are called meteorites. As we gaze across the solar system, it becomes clear that planets rarely travel alone. Most are accompanied by moons, natural satellites that come in astonishingly diverse sizes, compositions, and histories. These aren't just ornaments orbiting planets. They are miniature worlds, each with stories to tell about the processes that shaped our cosmic neighborhood. Moons can form in several ways. Some arise from circumplanetary disks, rings of gas and dust that swirl around a young planet. In these disks, material gradually coalesces into stable moons, much like the planets themselves formed around the Sun. Others are born from catastrophic collisions. Earth's own moon, for example, is believed to be the result of a titanic impact between the early Earth and a Mars-sized object, which flung debris into orbit that eventually accreted into our lunar companion. Some moons, especially smaller, irregular ones, may have been captured objects pulled in by a planet's gravity from elsewhere in the solar system, a wandering asteroid or comet transformed into a permanent satellite. The giant planets host the solar system's largest families of moons, numbering in the dozens or even hundreds. Jupiter, for instance, has over 95 confirmed moons, from the volcanic hellscape of Io to the ice-covered oceans of Europa, where water may still exist beneath a frozen crust. Saturn boasts at least 146 moons, with Titan harboring a thick atmosphere and lakes of liquid methane, and Enceladus erupting plumes of water ice into space. Many of these moons likely formed alongside their planets within circumplanetary disks, while irregular outer moons may be captured fragments of distant asteroids or comets, illustrating the solar system's chaotic and dynamic past. Even smaller moons provide crucial insights. Some of Saturn's tiny satellites sculpt the edges of its rings, while Phobos and Dyma, Mars moons, may be captured asteroids offering clues about the early asteroid belt. Studying moons allows scientists to observe planetary processes on a smaller scale: volcanic activity, ice tectonics, tidal heating, and even subsurface oceans, all of which inform our understanding of planetary evolution and habitability. In essence, moons are worlds orbiting worlds, natural laboratories that preserve the history of collisions, captures, and cosmic chemistry. From the tiny irregular satellites to the massive ocean worlds of the outer solar system, they remind us that planetary systems are not static. They are dynamic, evolving, and endlessly fascinating. Each moon carries a piece of the solar system story, a chapter that complements what we learn from its parent planet. Scattered throughout the solar system, tumbling between planets, lurking in distant belts, or circling giant worlds, are thousands of asteroids, comets, and moons. At first glance, they may seem like cosmic debris, but in reality they are time capsules from the dawn of our system. Each one holds a record of the chemical ingredients and physical processes that existed long before Earth or the other planets took shape. Asteroids, with their primitive, unmelted interiors, are fragments of the building blocks that never quite assembled into full-fledged planets. Comets, made of ice and dust, preserve the frozen chemistry of the outer solar system, delivering water and organics to the inner planets in ancient times. Moons, ranging from battered little rocks like Phobos to ocean worlds like Europa, reveal how planets interact with their satellites and share material across space. By studying these bodies with powerful telescopes, robotic explorers, and sample return missions such as Hayabusa 2 and OSIRIS-REx, scientists can literally piece together the story of planetary birth. We learn how dust grains stuck together to form pebbles, how pebbles built planetesimals, and how migrating gas giants reshaped everything in their path. This knowledge doesn't stop at our own cosmic backyard. The same physics and chemistry apply to the thousands of planetary systems now being discovered around other stars. By decoding the messages locked inside asteroids, comets, and moons, astronomers are building a blueprint of how worlds form everywhere in the galaxy, an essential step toward predicting which of those worlds might be able to host life. In other words, the smallest and most overlooked bodies in our solar system may hold the biggest clues about our origins and our future place in the universe. Efforts to explore the solar system have undergone significant evolution since the mid-20th century. The period between 1976 and 1989 is often referred to as the golden age of planetary exploration, characterized by the deployment of sophisticated robotic spacecraft that yielded a wealth of information about various planetary bodies. This era marked a transition from guesswork to a more data-driven approach in planetary astronomy, leading to the emergence of comparative planetology, a discipline aimed at understanding planetary features such as atmospheres by comparing different celestial bodies. A notable phase in planetary exploration commenced with advanced spacecraft designed for orbital missions. Among the key missions were Magellan and Venus Express, focusing on Venus, Galileo Jupiter, Cassini Saturn, and Messenger Mercury. This renewed vigor in planetary exploration also included a consistent series of landers and orbiters sent to Mars, further enriching our understanding of the Martian environment. The Cassini spacecraft, launched in 1997, revolutionized the study of Saturn and its system. It was the first spacecraft to orbit Saturn and conducted extensive research over its 13-year mission, providing groundbreaking insights into the planet, its rings and moons, including the ocean-bearing moon Enceladus. In September 2017, Cassini concluded its mission by intentionally diving into Saturn to protect its moons from potential contamination, ensuring that future exploration could be conducted with pristine conditions. Future planetary exploration aims to continue this momentum, particularly regarding the ice giants, Uranus and Neptune, which have only been visited briefly by Voyager 2 in the 1980s. Several mission concepts are being discussed to explore these distant worlds, possibly adopting strategies similar to those used in the Cassini mission. Imagine the solar system nearly 4.6 billion years ago, a vast spinning disk of gas, dust, and ice surrounding the newborn sun. At first, it seems like chaos, a swirling cloud of microscopic particles. But within this chaos, the seeds of planets are quietly taking shape. This is the stage where the core accretion model, the leading explanation for how planets form, begins its story. In this model, the process starts with tiny dust grains colliding in the protoplanetary disk. These collisions, over thousands and millions of years, allow particles to stick together, forming larger clumps known as planetesimals. Think of it as cosmic building blocks, small rocks gradually merging into boulders, and boulders into planetary embryos. These embryos, through gravity and repeated collisions, grow larger, eventually forming the cores of full-fledged planets. For terrestrial planets like Earth, Mars, Venus, and Mercury, this process primarily involves solid materials, silicate, and metals, because the inner disk is too hot for ices and volatiles to survive. The cores slowly grow, drawing in nearby material until they reach their final rocky forms. For gas giants like Jupiter and Saturn, the story takes an extra dramatic turn. Once a solid core reaches a critical mass, roughly 10 times the mass of Earth, it begins to pull in vast amounts of gas from the surrounding disk. At this point, gas accretion accelerates sharply. Gravity essentially takes over, and the planet's growing envelope begins to collapse onto itself, rapidly forming the massive gaseous layers that characterize these giants. This self-amplifying process explains how enormous gas planets can form within the relatively short lifetimes of protoplanetary disks. Ice giants, such as Uranus and Neptune, form similarly, but in colder, outer regions of the disk. Here, heavier ices, water, ammonia, methane are abundant, contributing to cores with different compositions. Because the gas density is lower, these planets acquire smaller gas envelopes, giving them their unique, icy character rather than the thick hydrogen-helium dominance of Jupiter and Saturn. The core accretion model is elegant not only because it explains the planets in our own solar system, but also because it helps astronomers understand the diversity of exoplanets observed around other stars. It predicts why some planets are rocky, some gaseous, some giant, some small, and why planetary systems often form in specific patterns. Variations in disk mass, temperature, and composition can lead to hot Jupiters hugging their stars or distant ice worlds on wide, slow orbits. In essence, planet formation is a tale of gradual growth punctuated by explosive moments, where cosmic dust becomes worlds through a combination of patience, chance collisions, and the inexorable pull of gravity. From tiny grains to massive planets, the same physics shapes both our solar system and the countless planetary systems scattered across the galaxy. While the core accretion model explains much about planetary formation, astronomers have long known that it may not account for every type of planet, especially the most massive gas giants found both in our solar system and around other stars. This is where the disk instability model enters the story, a more dramatic, rapid mechanism for building planets. Imagine the early protoplanetary disk, a vast, spinning pancake of gas and dust encircling a young star. In some regions, particularly the outer, cooler reaches, gravity can take control in unexpected ways. If the disk is massive enough, its own self-gravity can overpower internal pressures and shearing forces, causing it to become unstable. In these unstable zones, the gas doesn't simply swirl in place. It can collapse into dense clumps, fragmenting into what could become gas giant planets almost overnight. Astronomically speaking, this is a far faster process than core accretion. Instead of slowly building a solid core over millions of years, and then gradually gathering a gaseous envelope, disk instability can produce massive planets in just a few thousand years. These newly formed giants may even tiptoe on the boundary between planets and brown dwarfs, objects too large to be considered planets, but too small to ignite sustained hydrogen fusion like a star. The physics behind this process is intricate. Cooling rates, turbulence, disk density, and temperature gradients all influence whether the disk will fragment or remain smooth. Typically, the outer disk, far from the star's intense radiation, provides the right environment. Here, the gas can shed heat efficiently, allowing gravity to win over thermal pressure, and the disk breaks into multiple clumps that collapse under their own weight. Disk instability also offers explanations for some of the more puzzling exoplanets we've observed. Extremely massive gas giants orbiting at great distances from their stars, far beyond the reach of traditional core accretion. These distant worlds, sometimes hundreds of astronomical units away, may have formed not slowly, but in a burst of cosmic clumping, sculpted by the raw force of gravity. In the grand story of planet formation, disk instability complements core accretion. Together, these mechanisms show that the universe has multiple ways to turn dust and gas into planets, and that the variety of planetary systems we see today, from compact rocky worlds to far-flung gas giants, reflects the richness and complexity of the processes that sculpted them. Recent advancements in observational techniques, such as disk imaging and exoplanet detection, have shed light on the initial conditions for planet formation, prompting a reevaluation of existing models. Despite the progress, substantial gaps in understanding remain. For instance, while the core accretion model has been foundational, discrepancies between theoretical predictions and observational data indicate that certain phases of planet formation are still not well understood. As researchers continue to investigate these phenomena, new models are emerging that integrate observations with theoretical frameworks to better explain the diversity of planetary architectures observed in the universe. Even with decades of research, detailed computer simulations, and observations of distant planetary systems, the story of how planets form is far from complete. While core accretion and disk instability provide powerful frameworks, astronomers still face fundamental questions that make this field one of the most dynamic in modern science. One key mystery is the role of pebbles in planet formation. These small, millimeter to centimeter sized particles may act as crucial building blocks, drifting through the disk and sticking together to feed growing planet cores more efficiently than previously imagined. The way pebbles clump, migrate, or evaporate under different disk conditions could dramatically influence the size, composition, and location of the resulting planets. Another challenge lies in understanding planetesimal formation itself. How do dust grains leap from tiny, slow-moving particles into kilometer-sized objects capable of gravitational attraction, turbulence, magnetic fields, and collisions all play a role, but the exact balance of these forces and how they vary across different disks remains uncertain. Beyond individual growth, interactions among multiple forming planets introduce additional complexity. Planetary embryos can scatter one another, migrate inward or outward through the disk, or even collide to create entirely new worlds. These dynamic processes may explain why planetary systems come in such astonishing diversity, from tightly packed super-Earths to widely separated gas giants. Finally, astronomers are eager to connect theory with observations of other star systems, advanced telescopes, and missions such as ALMA, Kepler, and the James Webb Space Telescope are providing glimpses of protoplanetary disks in unprecedented detail. We can now see gaps carved by forming planets, spiral waves in the gap, and even planets in the act of accreting material. Each discovery challenges our models and refines our understanding, showing that the universe is capable of forming planets in ways both familiar and unexpected. In short, planet formation is a story still being written. Every dust grain, pebble, and orbiting embryo contributes a line to this cosmic narrative. As our tools grow sharper and our observations expand to thousands of planetary systems across the galaxy, we move closer to answering questions that have fascinated humans for centuries. How do planets like our own arrive? How common are worlds capable of hosting life? And ultimately, how does the universe go from simple dust and gas to the rich diversity of worlds we see today? Thanks for listening this whole video. If you enjoy this video, don't forget to subscribe to my channel. Thank you.